In our group project, we used a Gaussian distribution to model the forcing profile of a horizontal axis wind turbine. My individual extension involves comparing a horizontal axis wind turbine to a vertical axis wind turbine. A gyro mill, as shown below, sweeps out a uniform cylindrical area. This means the forcing profile of the turbine can be modelled as uniform throughout. Whilst the top hat function may seem suitable for modelling this uniform distribution, it falls foul to one major issue.
The Gibbs phenomenon.
For any piecewise smooth function, there are errors around discontinuous points when calculating the Fourier transform. These errors, visible as an over and under shooting sine wave around the maximal amplitude point, have a magnitude proportional to the jump size. We need a model which eradicates these errors. The tanh function approximates the step, so we can estimate our uniform forcing profile with the below equation. This has the added advantage of being differentiable at all points, keeping it safe from the Gibbs phenomenon. As you can see, reducing the value of delta gives us a better estimation of our top hat function. The forcing profile in the x direction retains the same Gaussian distribution from our original model, since forcing still decreases as distance from the turbine increases. Meanwhile, the z direction is changed to our tanh-based equation, which more accurately represents the vertical axis wind turbine's behaviour on the surrounding air. To fairly compare the two models, we must equate the total frictional forces applied by the turbines on the air. Thanks to Newton's third law, we know that this is equal to the thrust applied on the turbine by the surrounding air. The total thrust acting on the turbine is equal to the sum of all the individual forces. Since our forcing profile is defined in both the x and z directions, the summation of forces will be across the entire area domain. The continuous nature of our function requires us to use integration to compute this. We use the ratio between the two thrusts to normalise our forcing amplitude. This equates the strength of the two turbines. Our group project used the centred difference method to calculate the partial derivative of fx with respect to z. Applying this method to our top hat function approximation would result in a loss of our desired continuous property, risking the return of the Gibbs phenomenon. Fundamentally, power is the product of force and velocity. To adapt this equation to work in our 2D space, where both force and velocity are matrices spanning a grid, we will calculate the power by integrating their product over the entire area domain. This is similar to what we did when calculating the total thrust. This equation can be used to calculate the power extracted by the turbine. However, in order to calculate efficiencies, we need to compare this to the total power available in the air. We use this equation to calculate this. Rho is the density of the air, S is the cross-sectional area, and U0 is the background wind speed. The below heat map shows the velocity reduction for a horizontal axis wind turbine. As you can see, the peak velocity reduction occurs at the hub height and gradually decays either side. This differs from the vertical axis wind turbine, which retains the same high velocity reduction throughout the entire height range of the blades, but rapidly reduces to zero outside of the turbine. Our calculated efficiencies are shown below. The horizontal axis wind turbine had an efficiency of 24.59%, whilst the vertical axis wind turbine was a much higher 43.93%. Both of these values lie below the 59.3% theoretical ceiling defined by the Beck's limit. No turbine, regardless of its mechanism, can operate at a higher efficiency than 16/27. One reason that the vertical axis wind turbine efficiency is higher than we may expect is because we have ignored backtracking. Since the blades move parallel to the wind, they need to do work against the wind at points in their rotation. For example here, if the wind were to be blowing into the screen, as the blades go into the screen, the wind is pushing them, but as the blades emerge back out of the screen, they need to do work against the wind. Horizontal axis wind turbines don't have this issue, since their blades are perpendicular to the wind. This means that in the real world, The wind extraction from horizontal axis wind turbines is often better than that of vertical axis wind turbines. Society's continued use of horizontal axis wind turbines is due to its mature technology and long record of operational success, as shown by these windmills in Zhangjiang, which date back to 1609.